All right, you may start.
Okay, so hello and thank you for the invitation. And our topic today will be solving a linear equation system in colorings of integers. My co-authors are Anita Liebenau and Natasha Morrison. And our friends always think that we spend our days solving long equations. And now today I'm actually going to justify their prejudice. So even though most of the talk is about linear equations, I'll actually start from graphs because, you know, I'm much less scared of graphs and it's also much easier for me to draw pictures. So we start from Ramsey's theorem. So we're considering edge colorings of a complete graph, and we're looking for a monochromatic copy of a given fixed graph H. So for instance, H could be a triangle. Now, Ramsey's theorem that says that as soon as your complete graph is large enough in terms of H, you are guaranteed to find a monochromatic copy. So as an example, here's a red-blue coloring of K6, and this is guaranteed to contain a monochromatic triangle. For instance, here you see a red triangle and another red triangle there. And that's actually, so that's guaranteed for K6, and that's best possible. So there are colorings of K5 with no monochromatic triangles. But now it's natural to ask, well, can we do this with fewer triangles? So can we achieve maybe just one monochromatic triangle? And perhaps more generally and more interestingly, as you let n tend to infinity, what is the minimal number of monochromatic triangles? Or what is the minimum number of monochromatic copies of a specific graph H? And now let me be boring and repeat this once again. It's important that the size of H here is fixed and n tends to infinity. And in this regime, actually by Ramsey's theorem, you are guaranteed a positive proportion of monochromatic H copies. So faced with this question, you would probably say, well, what about the random coloring? How does it perform? So here you take the edges of your complete graph and you just color them red, blue independently at random. And now the expected number of monochromatic triangles is actually a quarter n choose 2. That's because for each fixed, so there are n choose 3 triangles. And for each fixed triangle, so for any 3 points I choose, the probability that in this random coloring, the corresponding triangle is red is an 8, and the same thing for blue. So the total expected proportion of red triangles is a quarter, of monochromatic triangles. So this quarter I'll refer to it as the random benchmark. So that's what's achieved by a random coloring. And that's going to be relevant throughout our talk. And this, in fact, generalizes to any graph H. So for a given graph of fixed size and a given fixed copy of H, the probability that this copy comes out monochromatic is this, and then times 2 for the 2 colors. So altogether, this is, again, the random benchmark for a graph H.
So sorry, by density, you just mean the fraction of monochromatic versus all copies.
Yes, exactly. Okay. Yes, which is then my next remark. So you see here for triangles, we just counted triangles, but actually it's more elegant to just work with the density, because then you don't have to worry about this normalization. You can just say for each triangle, what's the probability that it's monochromatic, and that's your expected density of monochromatic copies of H. So again, throughout this talk, we'll work with this density. And actually, all our colorings would be red and blue. So it'll always be just 2 colors, not more.
So EH is the density, E of
EH is the number of edges in H.
Okay.
So for a triangle, this will be 3. The triangle will have 3
Right.
edges, so the corresponding benchmark will be a quarter. Okay. So thanks for your questions, and please do ask questions throughout the talk. And by the way, I will switch to the whiteboard later. I won't throw 1 hour of slides at you. Okay, so this is our random benchmark. So this is what's achieved by a random coloring. And now the question is, are there colorings which beat this, in the sense that are there colorings with significantly fewer monochromatic H copies? And in fact, Erdős conjectured that when the small graph is a clique, the answer is no. So he actually conjectured that there are no graphs for which there are no colorings which perform better than the random one for cliques. And this is partly motivated by the fact that random is the best we know in many Ramsey theoretic problems. Specifically, if you want lower bound for this Ramsey number, then the best we know how to do is the random coloring. And Boer and Drosta were even more ambitious. They conjectured that this is the case for all graphs H, so not just cliques. Okay, so that's our question. So once again, we're trying to minimize H copies, and conjecturally, the random coloring is tight. So what do we actually know? Well, this the Boer-Drosta conjecture is actually true for triangles. So random is optimal. This was known even before. It's a classic theorem of Goodman. And it was actually motivation for this conjecture. So Goodman's theorem was known before this whole line of questioning. But that's more or less where the story stops when it comes to cliques, because Thomasson showed that it's already false for K4. So let me draw a picture. So for K4, there are colorings which outperform the random one. And then there's a vast extension of this theorem. So Jagger, Storycheck, and Thomasson show that in fact, that just containing a K4 is sufficient to violate the Boer-Drosta conjecture. So if I give you any fixed graph H and you see a K4 in it, this is already enough to violate the Boer-Drosta conjecture. And notice that this is highly non-trivial, so there is no obvious monotonicity in this problem. So it's not obvious how to take a coloring which is somehow bad for K4 and then turn that into a coloring which is bad for a specific graph H. So again, for this graph, the conjecture is false. And that kind of implies that this conjecture is false for most graphs H, because most graphs H will contain a copy of K4. Does that make sense?
So in particular, Erdős's conjecture is also false. That's what?
Yes, exactly.
Right.
Yeah. So for all cliques larger than 4, this is false. So you may ask, well, you know, why is this interesting when it's false for most graphs? But actually, it then motivated a whole area of research on common and Sidorenko graphs. So there are many classes of graphs for which this is known to be true or false, and there's the famous conjecture of Sidorenko that's kind of related. But again, today it would just be great if you can memorize this picture, this theorem of Jagger, Storycheck, and Thomasson, and I will stop talking about graphs now. So this was kind of a quantitative extension of Ramsey's theorem. But actually, you can take your favorite coloring result and extend it in this direction. So specifically, Schur's theorem tells you that any monochromatic coloring of the integers contains a Schur triple, which is a triple satisfying this equation. And then it's natural to ask, well, if you then let n tend to infinity, what is the minimal density of monochromatic Schur triples? And the same thing for instance, k-term arithmetic progressions. So this would extend van der Waerden's theorem, or actually your favorite arithmetic structure. And this was indeed asked for Schur triples by Graham, Rado, and Ruchinsky. So they asked, so we're given an interval 1 up to n, and their question was to minimize the density or the number of monochromatic Schur triples in this interval. And notice that in this question, the way they ask it, there is no wrapping around. So it's just the interval 1 up to n. And this was soon thereafter answered in 3 independent papers. And this is the asymptotic answer for Schur triples. But again, a key component of this problem is actually that there is no wrapping around, and that makes the problem more difficult. When you actually go to the group setting, the question becomes much more general, but also much simpler. So now actually we can consider any abelian group instead of the interval. So for instance, you can consider Zn if you don't like groups, so integers modulo n. And Cameron, Ciruelo, and Serra showed that any red-blue coloring will contain at least this many monochromatic Schur triples. And notice that this 1/4, I'll show that on the next slide, but this 1/4 is actually the random benchmark for Schur triples. So that's the expected number of Schur triples in a random coloring of this group G. And again, G squared is just the normalization. And for the rest of the talk, I won't bother with that. We'll just be looking at density. So this theorem shows that for Schur triples, random is optimal, informally. And in fact, their result extends to any odd equation, so any equation on an odd number of variables. And that includes, for instance, 3-term arithmetic progressions. So this equation describes 3-term arithmetic progressions. And for them, the random coloring is optimal. Okay, so the random coloring is optimal for any odd equation. What about then general equations? So let me finally now make some definitions and define our setting. So we'll be considering linear equations denoted L of x with coefficients in a finite field. So this is the so-called finite field model. And by the way, all of our equations, all of our systems will be homogeneous. So the right-hand side will be just 0. And again, our coefficients are in a finite field fq. So q is a prime power, and our solutions lie in fq to the n. So this is perhaps not a setting you're used to. So q is a prime power. It's very convenient for this type of problems because FQN has a nice abelian group structure, but also a natural way of n tending to infinity. So we want asymptotic results as n tends to infinity. But also these coefficients A1 up to AK are constant. So A1 up to AK are constant in a finite field, but the solutions are in this abelian group. Okay. And we define an equation to be common if the density of monochromatic solutions is at least this 2 to the 1 minus k in any coloring of the integers, in any coloring of the of fq to the n of our abelian group. And once again, that's the random benchmark. So this name common comes from the fact that the solutions to L are actually fairly common. And let me just give an example. So, for instance, a 4AP is just described by two linear equations. So that's a 4-term arithmetic progression, -2, 1. And more generally, if you want a k-term arithmetic progression, then you give yourself k variables. 1, so this is k variables. And this describes a k-term arithmetic progression. And what is the expected, in a random coloring, what's the expected density of k-term arithmetic progressions? So it's just the way we had it with graphs. So the probability for each fixed k-term arithmetic progression, the probability that it's red is asymptotically 2 to the minus k, and the probability that it's blue is also 2 to the minus k, which then in total gives us an answer 2 to the 1 minus k. And here I need to be, if I want to be completely rigorous, I'll add a little of one term. So here a little of 1, I mean as n tends to infinity. And why do I need that extra term? Well, that's because there are some boring arithmetic progressions, for instance, the constant arithmetic progression, for which this calculation is not true. But most arithmetic progressions are actually interesting, non-degenerate, so they have k distinct components. So this is the correct expected density. Okay, so does this definition make sense? So that's, again, an equation is common if the density of monochromatic solutions is at least 2 to the 1 minus k. And now, so this motivation, I'm gonna actually, let me erase this ink. I actually rushed ahead of myself and showed you all the definitions for equations, for systems of equations before, well, when I should have just talked about single equations. But anyway, so now I meant to tell you the result about single equations first, and then we'll go back to systems of equations. Sorry about that. So this is the definitions for the definition for a single equation. And now we've seen already that for odd k, so for odd number of variables, all equations are common. But now, in case you had any doubts about the interestingness of this definition, here's a very nice characterization of exactly which equations on an even number of variables are common. So common equations have exactly this specific symmetric form. Oh, sorry. Common equations, yeah, they have exactly this specific symmetric form, where coefficients come in pairs which sum to 0. So up to reordering, again, the coefficients just come in inverse pairs, and that describes all the common equations. And this theorem was shown, one direction was shown by Saad and Wolf. So Saad and Wolf showed that equations of this form are indeed common, and Pham and Zhao showed that showed the converse. So they showed that for any equation that doesn't have this form, there are colorings with too few solutions, so with fewer solutions than expected. So again, that's a very interesting direction because you need to show it, you need to find a coloring for any equation. And Pham and Zhao actually do it with a randomized coloring. So they come up with colorings based on Fourier coefficients. And I'm going to show this, this construction later in the talk. Okay, so that's now a full characterization of equations. And now a natural question to ask is, what about systems of equations? Okay, so both of these authors, Saad, Wolf, and Pham and Zhao, they all asked, can we have a similar equation, characterization for systems of equations? And there, a first kind of example would be K-term arithmetic progression. So here comes the definition that I rushed ahead. Now we replace a single equation by a K-variable system L. And this system is defined to be common under completely the same conditions. So if the density of monochromatic solutions in any two coloring is at least 2 to the 1 minus k. And I already gave you an example of K-term arithmetic progressions, and I kind of hand waved that this is indeed the correct random benchmark. So whether it's about equations or systems, what we care about is the number of variables k. Okay, and again, one example of a system is a K-term arithmetic progression, and here's a picture of a 4-term arithmetic progression. So that's our question for this talk. What can we say about systems of equations? When are they common? And so far, only sporadic results have been known. So nothing in this direction of Pham and Zhao, nothing very general like that, just looking at specific systems. So what is known? Well, it's known that 3-term arithmetic progressions are common. I've shown you that. However, already for k equals 4, Saad and Wolf found colorings of f5 to the n with fewer than expected 4-term arithmetic progressions. So when I say fewer than expected, it's just this small factor. So actually, you can see that it's pretty hard for systems to be uncommon. Usually, this discrepancy is not huge. And that was everything that was known about 4-term arithmetic progressions. But actually, again, the research doesn't stop there because it's still interested to ask what is actually the minimum. And there was a lot of work on that by various authors. And what about longer arithmetic progressions? Well, there's no obvious monotonicity there, but actually we've shown that for k at least 5, K-term arithmetic progressions are uncommon. And this was shown independently by Leo Verstegen. So this is kind of reminiscent of this result of Jaeger, Stovicek, and Thomason for graphs. But actually, there's another parallel with that. Well, because actually, note that a K-term arithmetic progression contains a 4-term arithmetic progression. And actually, this was all that we used in our proof. So what we actually can show is that any system containing a 4-term arithmetic progression is uncommon. So I'm not going to define this containing a 4-term arithmetic progression because this theorem is not the main focus for today. It's just kind of, again, a parallel to this Jaeger, Stovicek, Thomason result and something that people actually asked about. So what I want to focus on today is a much more general theorem, which also has a lot of room for improvement. So yeah, maybe you can push some of these ideas further. So I'm just going to state this theorem with some unknown words to convince you that it's fairly simple in general, and then we'll go to the whiteboard and define everything we need. So our main theorem for today says that if L is a system of even girth, again, something I'm about to define, and we want to deduce that L is uncommon, it's actually enough to look at certain critical equations of L. So what I want you to take away from these slides is that it's enough to deduce uncommonness of L just by looking at single equations. And we know that single equations are easy because of this result of Fuchs, Pham, and Zhao. So it's enough to look at their coefficients and check if they come in matching pairs, and we can certify uncommonness. Okay, so that gives us fairly general families on uncommon systems, but now let me transition and actually show you the necessary definitions. Okay, so here's our, please can you tell me, can you nod if you can see the whiteboard? So if you can see
I can see the whiteboard, yeah.
Okay, thank you. So this is just a restatement of the theorem. So we're interested in what girth is and what critical equations are. And the girth of a system L is actually the number of variables in the shortest equation that can be derived from L. I can see a typo here already. So the game is basically, you look at the matrix for L, we'll see some examples. You look at the matrix of L, you try to eliminate as many variables as you possibly can, and then the length of the shortest equation will be the girth of L. Okay, and these shortest equations, which certify the girth, they're called critical equations of L, and they're denoted C of L. So let's look at some examples. Here's a system with, sorry, just still. So here's a system L1 with 2 equations, 6 variables. Again, the coefficients are in a finite field, but please imagine that this field, the size of this field Q is at least, say, 11, because I don't want you to come and say, oh, actually, isn't 3 equal 0? So that's a system. And I'm claiming that this is the shortest equation you can possibly derive from L, and therefore this equation will be its critical equation. And I'm claiming that the system has girth 4. Okay, so how can we see that? Well, if we try and eliminate any other variable, so let's say we try to eliminate x4, then we need to sum up these 2 equations, and we actually end up with 5 non-zero coefficients. So the best you can do by eliminating the variable, the 4th variable is length 5. And the same thing for any other variable. So if you try to eliminate any other variable, you would get an equation of length 5. One way to see this, again, elementary in linear algebra, is that all 4 of these columns are linearly independent. And the difference is that these first 2 columns are linearly dependent, and that's why you can eliminate x1 and x2 simultaneously. But anyway, that's just basic linear algebra. So these critical equations can just be obtained by performing row operations on L1. Here's our second example. So this is, again, a system on 5 variables, 2 equations. And in this case, I'm actually claiming that this system also has girth 4. In other words, I'm claiming that these are the shortest equations you can possibly obtain from L2. And again, the way to see that is by attempting to eliminate all other variables. So here we try to eliminate x3, x4, x5. And in each case, we ended up with 4 other non-zero coefficients. So all 5 of these equations are actually critical. So in this case, we have 5 critical equations. Equals 5. Okay. So are there any questions on this definition of girth in critical equations? Okay, looks like not. So let me just then give you a couple more examples. So here's already another system, L3. This is a similar type of system where, again, its girth is 4. And I'm not going to check this time, but it's not hard to see that it has 5 critical equations. And in fact, all 5 of these critical equations are uncommon. So now let's go back to our theorem and see what it actually means and how we can use it. So here's our theorem. We have a system of even girth. And then if we look at all the critical equations and they're all uncommon, then the system L is uncommon. So let's see for which systems our theorem applies. Well, this is an example of girth 4, so even girth, check. And we have one critical equation, 1, 2, 3, minus 6. And this critical equation is uncommon because, again, the coefficients don't come in plus minus pairs. So altogether, our theorem 2 implies that this system is uncommon. Okay, for L2, once again, we have girth 4, but when we look at the critical equations, we actually have 2 uncommon critical equations and we have 3 common ones. So we actually can't deduce anything about this from our theorem. However, for L3, we have a similar situation. Girth 4, sorry, we have girth 4. We have 5 critical equations, but these are all uncommon. So actually, our theorem then implies that this system is also uncommon. And there's one final example, just in case you still didn't get a feel for these things. Here's an example of a 5-term arithmetic progression. This system has girth 3. So that's odd girth. So our theorem doesn't a priori apply to this system. However, we've seen earlier in the talk that this system is also uncommon. Okay, so that was the statement of our theorem. Again, we reduced the uncommonness of L to looking at single equations. But if this condition feels a bit too strong, then you have the right intuition, because as we saw here, well, what if some of the critical equations are common, some are uncommon, etc. Can we still say something? And our next theorem is actually a kind of general superposition tool. So I'm saying superposition because you can look at these critical equations and superpose them together. And you can use that kind of intuition to produce bad colorings. So let me state this more general result. So this is once again the restatement of the theorem that I've just shown you, theorem 2. And now again, to state this, this more general superposition tool, I need a bit of notation. So I'll just define the density of solutions that we care about. So for system L, And for a coloring of fq to the n, or rather for a subset of fq to the n, we denote the density of monochromatic solutions by lambda L of A. I'm just still doing technicalities, sorry. Okay. So the density of monochromatic solutions in A or in A complement is denoted by lambda L of A. So now I've passed to subsets of FQ to the n that's completely equivalent to colorings. So if I have a coloring, I denote the red part by A and the blue part by A complement, and then I count solutions with all components in A or in A complement. So this lambda is the density of solutions to L in A. So that's in the red part, or in A complement, which is the blue part. So that's the density that we care about. And then I'll just subtract the random benchmark because that makes everything more elegant. Okay, so this is just notation again. So our definition of commonness says that L is uncommon if and only if there is a set A, which again corresponds to a coloring, such that this lambda L of A is negative. Lambda L of A is negative. So once again, this is just the density of monochromatic solutions in the coloring A. So this whole thing is just a restatement of my, my definition. And here, formally speaking, I also need to say there exists an N, because again, this coloring lives in a universe FQ to the N, but that's yeah, something we often glance over. Okay, so that's just a restatement, and now this allows us to state the second theorem. 3. So we're still assuming even girth. L has even girth. And we suppose that there is an integer n and a coloring of fq to the n, such that, now this is important, we'll look at the contribution of critical equations of L, and we count how many solutions to each critical equations we have, to each critical equation we have, and if that's negative, then L is uncommon. So I'll meditate on this a little bit because I'm aware that it's a bit of a mouthful. So again, here this sum is a kind of superposition of the contributions of the critical equations. So here again, we're looking at M, and M is a single equation, which is derived using these row operations from L that we just did on the previous slide. So if we have a coloring in which the sum total of these of the solutions to these critical equations is negative, then we can deduce that the whole system is uncommon. And this is important again because the size of L can be arbitrary. So L can have 100 variables, 100 equations, and we're able to decide uncommonness based on just its critical equations. So just in symbols, in case this conclusion is clearer, what we actually show then is that then there is another certificate A prime that shows the uncommonness of L. So this A prime can be and is in general different from this, this certificate A.
Can I briefly ask a question?
Yeah.
So is the main difference between theorem 2 and theorem 3 now that the certificate for the uncommonness of the critical equations has to be the same for all in theorem 3, whereas in theorem 2 it could be different witnesses, or?
Yes. Yes, exactly.
Okay.
So yeah, that's the difference. But actually, yeah, that's what I was about to say. It's so theorem 3 is seemingly stronger than theorem 2. But in order to derive theorem 2, we need to somehow come up with these certificates, which are common to all the critical equations of L. So yeah, let me say this discussion in a bit more detail. So once again, which of these two theorems seems stronger? Well, a priori, theorem 3 looks stronger because in this case, in this sum, we don't require each of these terms to be negative individually. What we have is these critical equations, and there's a kind of fight among the critical equations, and then if the negative ones win, then the whole system is uncommon. So that's somehow less strong than this, because in this one we require all the critical equations to be uncommon. However, if you tried to naively derive theorem 2 from theorem 3, then you would say, okay, well, this L is a system whose all critical equations are uncommon. Therefore, let us take a certificate for their uncommonness, put it into this equation here, and decide uncommonness of L. But that's, of course, cheating because we don't have a common certificate for L, and that's kind of the challenge in this proof. Okay, so that's a comparison between these two theorems, and I'll show you later how to deduce theorem 2 from theorem 3. But this theorem, so why is this theorem 3 useful? Well, first of all, it has some useful consequences that I'm about to show you. But secondly, it's useful because it unlocks some methods that were previously unavailable to us. So specifically in studying single equations or four-term arithmetic progressions, people used methods from Fourier analysis that don't a priori apply to larger systems. But now when we have something like this, so when we have the decomposition in terms of single equations, this suddenly unlocks the use of Fourier analysis. And a third possible question is, well, how do these critical equations come into play? What's special about them? And also, how do they come in independently? Because somehow in this sum, it doesn't matter at all how the different critical equations relate to each other. And that's sadly something that I can't answer. It's kind of buried in the proof. I can't say a hint, however. So the reason that these critical equations make a difference is that if you solve, if you fix a specific solution to a critical equation, then you can uniquely extend the solution into a solution to the whole system. This is not the end of the story because you don't know whether this extension is red or blue, but at least it shows you that somehow these critical equations may be relevant. Okay, so that's it about theorem 3. Once again, the only important takeaway, it reduces the uncommonness of L to its critical equations. And now I want to show you how 3 implies 2. So we're on a quest of looking for these certificates. And there we build on this idea, this beautiful idea of Fox, Pham, and Zhao that I want to show you. So Fox, Pham, and Zhao, we'll stick to the case of 4 variables. I think that's illustrative enough. Fox, Pham, and Zhao, and kind of in conjunction with Saad and Wolf, they characterized single equations. So let's go back to single equations. This is a single homogeneous equation M. And they said that this equation is common if and only if the coefficients come in these inverse pairs up to reordering. Okay. So to show this proof, I need one isolated fact from the discrete Fourier analysis. So this is not even worth the name crash course. It's just one isolated fact. So I hope that it won't scare you. This will all be very hand wavy, but you can see how powerful and useful these methods can be. So what we're going to use is that any coloring of an abelian group, in this case fq to the n, can actually be represented in terms of the Fourier coefficients of A. So A hat, the Fourier coefficients, they're actually, you can think of it as a function from fq to the n to the complex numbers, or just a list of complex numbers that somehow describe this coloring A. So a bit more explicitly, again, each R, strictly speaking, each character R of this group gets a coefficient A hat of R. So you can think of this as a kind of change of basis. So here you have a binary representation of A in what we usually call the physical space. And here, instead of this binary representation, you have a list of Fourier coefficients. But now, the reason that this specific representation is useful is that now suddenly you can easily count the solutions to any linear equation. So given this equation M, the number of solutions to A is actually just this function of Fourier coefficients of A. So it's the sum over all non-zero characters of A hat of A1R times A hat of A2R, etc. A4R. So again, let's just stare at this sum for a bit. So R again takes any value in any non-zero value in fq to the n, and as R kind of runs through the group, then this first argument A1R also attains each value in each non-zero value exactly once, and the same is true for the second, third, and fourth summand. So it's a fairly structured function of our Fourier coefficients of A hat. So this is one important property of the Fourier transform that we need. And that's why, again, you can think of it as a kind of change of basis, a bit like diagonalizing a matrix. You switch to a different basis and suddenly your problem becomes much simpler. Another important property of Fourier coefficients that we use is conjugation. Oh, sorry. So what this transformation does, the way it acts on minus R, is that it just conjugates A hat of R. So this just comes out of the definition, and these two are the only properties of the Fourier transform that we're going to use. Okay, so now how does this proof of Fox, Pham, and Zhao works? Or actually first the Saad-Wolf. So let's first show this direction. So if the coefficients come in inverse pairs, then the system is common. Well, for each R, assuming that assuming this relationship between coefficients, this lambda m of a, actually not for each R, so this lambda m of a is just the sum of a hat a1 R, but then the second summoned, or the second term in the product, because a2 is minus a1 R, what we actually can do by the conjugation property is we can just replace this by a conjugate, get rid of this minus. And we do the same thing for a3 and a4. This is again just the conjugate of a3R, a3R. So this whole thing is non-negative. Why? Again, this is just the modulus of a complex number, so the whole sum will be non-negative. And this is true again for any A. So the equation is common. M is common. Okay, so that's the positive direction. Now for the negative direction, what do we need to do? The negative direction is a bit more tricky, and I'll do it in a sketchy way. If we want to use this, what we need to do is first make this right-hand side negative, and then we need to translate that back to the physical side, so back into a coloring A. And the second step is something I'm not going to show. So first, the first step is going to be find a hat such that this sum over R of the Fourier coefficients is negative. And then the second step will be to take this A hat and translate it back into a coloring of FQ to the N. And this actually, strictly speaking, can't be done, because when you apply, you take a hat, you apply the inverse Fourier transform, you actually get a function rather than a set. But this is a very neat but standard trick in additive combinatorics. So I'm going to focus on this first step, how to find the A hat, which make this entire thing negative. And that's the really nice idea of Fox, Pham, and Zhao. So I'm going to denote this entire term by YR. So for each R in the group, for each non-zero R, this will be a separate value YR. So what Fox, Pham, and Zhao do, they say is take these Fourier coefficients at random. So to be, say, plus minus beta, beta is some positive real value, uniformly at random, but respecting the conjugation property. That's important later when you want to, so in this second step, when you want to invert A hat. So what does that mean? Really, for each R, you flip a coin, plus minus, and you draw the corresponding Fourier coefficients at coefficient at random, but you need to be careful because R and minus R actually share the same coin. Okay, so now we have this random list of numbers, and now this sum, so each YR becomes a random variable. And this whole sum becomes a random variable, and we need to find at least one point where this random variable is actually negative. And that's the way we'll do that is again in two steps. So for step A, we argue that the expectation of YR is actually 0 for each R. And the way you argue that is, again, these are kind of 4 coin tosses. And you argue that at least one coin toss is independent of the others. And this coin toss that's independent, it comes out with plus beta or minus beta uniformly at random, and it makes the expectation 0. I'll go back to this briefly later. So by linearity of the expectation, we conclude that the sum over all R's of these random variables is also 0 in expectation. So what's the problem we are left with? Well, we have this random variable, which is the sum of YR's, and we know that it's centered at 0. This is 0. We want to find a negative value. So there's an unknown distribution. We want to find at least one negative value. But actually, then it's sufficient to find at least one positive value, and that's what we're going to do. So we're going to say that for A hat R, when A hat R is identically beta, which is bigger than 0, then we actually have that YR is beta to the 4th for each R, and therefore the sum is negative, is positive. The sum is positive. So we found one positive point in this probability space. And then expectation just implies that there is also a negative point. So there is a hat such that the sum is negative. So once again, what we did here was we didn't know whether this region of the probability space was empty, but what we could find is a positive point here, and therefore conclude that there has to be a negative point. In other words, we just show that this random variable is not just trivially 0. So you can imagine that maybe much more fancy analysis can be done there, but we needed this just one point, and that's what we got. Okay, so briefly on this point A, because this is where we actually use the assumptions on the coefficients. So the key observation was that this random variable YR has 0 expectation. And there we kind of picked out one coin that's independent of the other 4. This didn't work in the first case, so in the positive case, remember, because we had these coins kind of matching up. So we had these 2 coefficients and these 2 coefficients that come in pairs, and these pairs always make the variable YR non-negative. But actually, this is kind of the only obstruction, and you can show that in all other cases, this expectation is 0. That's kind of the engine of the proof. So that's the proof of Fox, Pham, and Zhao. And again, this characterizes the single equations, and it's based on sampling random Fourier coefficients. Are there any questions of this proof? Okay, so let me just say then briefly how we can deduce our theorem from that. So again, what was the challenge? We had I'll just write on the side. So we had theorem 2. And so we had a system whose all critical equations are uncommon, and we needed to find a certificate that kind of beats all of these critical equations at once. So here's an argument how 3 implies 2. And this common certificate will be exactly stolen from the Fox, Pham, Zhao construction. So we'll take A from this randomized construction of Fuchs, Pham, and Zhao. And then you can't actually black box it. You need to go through the analysis again and add a line or two, but it's really not complicated. What you need to use is that because by assumption of theorem 2, each critical equation of L is uncommon, then this contribution, this expected contribution of M is 0. And then in a sum total, the contribution of the critical equations will be 0. And then you'll have this one positive point that it's in common to all the critical equations M, regardless of their coefficients, and therefore you find A such that the sum over the critical equations is 0. And then theorem 3 implies that L is uncommon. Okay, so that's just a very brief sketch, but yeah, please let me know if any of that proof is doesn't make sense. Okay, so that's the end of the kind of proof sketch that I want to show you. So going back to the conclusion, so just recapping what I just said. So the main point of our talk of this theorem was that once again, suddenly you can steal techniques from Fourier analysis and things that work for a single equation and apply them to large equation systems. So conclusion, we had this superposition theorem. And actually, this kind of superposition tool works for all systems L, not just even girth, but you need to do a bit of extra work in defining and setting up these critical equations. An open question is then, so there's a lot that's open in this area, but one obvious thing from my presentation is what if this critical set of equations contains both common and uncommon equations. And uncommon equations. So let me just show you an example briefly. So going back to our examples, even in case of two equations for variables, the situation is unclear. So for instance, we had this one system that had two uncommon critical equations and three common ones. And it actually turns out that that thing is common. That's one of very rare, I'd say, common systems, because there are some funny coincidences among the coefficients. So I'm not going to go into detail now, but I wrote actually what this lambda L of A is. Again, you can do that in terms of the Fourier coefficients of the critical equations. And then you can apply Cauchy-Schwarz to show that these common critical equations actually beat the uncommon ones. But again, to me, that seems as quite a unique kind of situation. But at least we know that not all the systems are uncommon. Okay, so that's one example with kind of mixed critical equations. Another example here below, which is perhaps more typical, I wrote it here, is where you have this one common critical equation. And the remaining ones that I won't write out, you have 4 uncommon critical equations. And this kind of theorem can also be shown to be uncommon using the stronger theorem 3. But you need a kind of ad hoc construction. At least we did it with an ad hoc construction. So you manually construct these A hats and you say, okay, the Fourier sum is negative, but it's again very ad hoc tailored to this specific system. So the question is kind of, are there general arguments that work for a larger class of systems that look a bit like this? And one possible approach is, again, going back to this construction of Fox, Pham, and Zhao, and analyzing the distribution more carefully. So my question is, what is the distribution of, let's have a specific example, say this thing, when again the hats are taken uniformly at random with, say, a hat of R plus minus 1, say, uniformly at random. I don't know. It could be asymptotically normal, but again, I don't have a proof. Okay, so that's all I'm going to say for today. And I need to acknowledge my European Union funding and also thank all the institutions that supported us while we were doing this long distance research. And thank you again for the invitation and for listening.
All right, thank you very much. Are there questions for Nina?
So these Fourier analytic techniques, don't they exist for any abelian group? I mean, so Fox, Pham, and Zhao, they only showed it for FQN?
So actually, yeah, thank you for your question. I forgot to say, so Fox, Pham, and Zhao showed it for FQN. But yes, these Fourier analytic techniques exist for all abelian groups. Let me just go to this slide that was here. Right. Yes. So actually, I have to say, Leo Verstegen showed independently. So he extended this Fox, Pham, Zhao result to arbitrary abelian groups. So that's another very interesting paper, and it's not straightforward. So actually, the obstacle here to general abelian groups is in this step 2. So yes, you can construct for any abelian group, you can construct these random Fourier coefficients, A hat. But the problem is that somehow in a general abelian group, when you try and take that back into a coloring, yeah, I'm not going to go into detail, but you get a sampling error that's too high. So basically the second step doesn't work for an arbitrary abelian group.
Thank you.
Any other questions? So I have one. In case that something is uncommon, like how far from being common can it get? Are there any bounds known as to how worse this can be, and how bad it can be?
Yeah, that's another very interesting question. So again, people looked at this for 4-term arithmetic progressions. So there are some interesting papers due to, again, Saad, Wolf, and Gowers, and the other people I had on slides. So yes, for 4-term arithmetic progressions, but usually it's some term of order, 10 to the minus 10 or something like that. It's not super clear. Now, one case that I think would be doable and interesting is single equations. So even for a single equation, I think it's not known. That would be really closely related to analyzing this thing. So the question would be, how do you minimize that thing?
Mm-hmm.
But once again, the extra added difficulty in that is that even once you minimize this, so for an arbitrary function a hat, you still need to make sure that those are actually Fourier coefficients of some sensible function or set A, and that puts extra constraints. So that puts constraints on your a hat that are not somehow straightforward in trying to do some optimization.
Are there some like almost trivial lower bounds on the number of monochromatic solutions that you get? I mean, apart from one, I guess.
Okay. So there's definitely bounds on the density. You can just those are kind of standard Ramsey theory arguments that if
Okay,
you
so they already
your
give you
n,
some lower bounds.
yeah,
that are,
yeah. So
okay,
if
I see.
increase your n enough, you get a positive density.
Okay.
Trivial bounds. They depend on the system, really,
Okay.
or on the equation, so on the coefficients of the equation. So that's, but yeah, it's an interesting thing to look at. So for instance, an equation that just has coefficients 1, 1, 1, 1, I think is not too hard to get some bounds by hand.
Okay, thanks.
And can I say, by the way, on that note, so trying to minimize the number of copies, that's also very interesting for graphs and not known. So for instance,
Okay.
monochromatic copies of K4,
Mm-hmm.
again, some very nice papers there, not known.
Let's see.
And sorry, another question. So, and have equations in non-abelian groups been studied also, or just like, I mean, instead of suppose you take, I mean, I don't know. I mean, you are taking arithmetic progression, but you can take x1, x2 equal to x3 or these sort of things. So, I don't know. These sort of equations.
Yeah.
Have you studied these sort of things? Or...
Yeah, I think a lot of this makes sense. However, yeah, I can't think of any specific results. What I do suspect is, in fact, that this direction may work. So we can have a look at that. So the positive direction, where is it? Yes, this positive direction here, because actually this thing you can show in an elementary way by not using Fourier, Fourier analysis. So for instance, okay, let me write here. So for instance, the equation, the additive quadruple, which is this, in abelian groups. Again, you can take that to a non-abelian setting. You can show fairly easily using Cauchy's inequality that that this thing is common, and that kind of thing may work for non-abelian groups.
All right. Are there any other questions still? That doesn't seem to be the case. So thank you again, Nina. I will stop the recording.